Okay, so this is the answer key to the Unit 1 review. I'm just going to go through the problems and the content you would need to know to answer each one of these. So for our first problem here, it says the graph of function f is shown above. What is the limit as x approaches 2 of f of x? In order to find that, you need to find two things. You need to find the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. And to find both of those things, you are going to look at your graph here where x equals 2, and you're going to see as it approaches from the left, what y value is it approaching, and as you approach from the right, what y value you're approaching. And you can see from this graph, from the left it approaches the y value of 4, and from the right, it approaches the y value of 4. So the answer to this question is C. It does not matter the fact that this has this removable discontinuity here. The actual value of the function at 2 does not matter at all when you're finding the limit. That just matters whether or not it is continuous or not. So this function, since the limit is not equal to the value of f of 2, would not be continuous. But the limit as x approaches 2 would be 4. For number 2 here, we have a similar situation. We're asked to find the limit for the graph of the function f. What value of a does the limit as x approaches a of f of x equals 0? So here, again, x approaches a. We're looking for a value of x where f of x is going to approach the y value of 0. So if we look at our graph, again, the limit as we approach from the left and the right both have to be 0 as we get closer and closer to whatever value we're looking at. As you can see that there's two values where that happens. At 2, as we approach from the left, the y value gets closer and closer to 0. As we approach from the right, the y value gets closer and closer to 0. And the same thing at 4. As you approach from the left, you head to 0. As you approach from the right, you head to 0. There are two other candidates that could mess you up, 0 and 1. The problem with the value, if we say a is equal to 0, as the x approaches 0 from the left, you do approach the y value of 0. But as x approaches 0 from the right, you approach the y value of -1. Since those do not agree, that limit as x approaches 0 does not exist. And at x, if you say a is 1, as you approach 1 from the left, you get to -1. As you approach 1 from the right, you get to -1. So the limit as x approaches 1 would actually be -1, not 0. Again, the actual value of f at any of those points doesn't matter. It just matters what it approaches from the left and right. So for number 2, your answer is B. For 3 here, we have the function f is continuous and increasing for x is greater than or equal to -1. The table above gives values at selected values of x. Which of the following is the best approximation of the limit as x approaches 0 of not f of x? The key thing is it's the limit as x approaches 0 of e to the -2 f of x. So in order to find that, we're going to work inside out. The first thing you have to find is what is the limit as x approaches 0 of f of x. And to do that, we look at the table. As x gets closer to 0 from the left, it appears like our numbers get smaller and smaller and smaller, so we can say they approach 0. As x approaches 0 from the right, you can again look at our y values here and notice that they get smaller and smaller and smaller as well, and it approaches 0. So we're going to say the limit as x approaches 0 from the left and the right are both 0, so the limit as x approaches 0 of f of x is 0. So then the question becomes, if f of x is approaching 0, what is the limit as x approaches 0 of e to the -2f of x? Well, that's going to be the same thing as the limit as x approaches 0 of e to the -2 times 0, which is the limit as x approaches 0 of e to the 0. And e to the 0 is a constant. It's just 1. So the answer to this problem is just 1. All right, next one. Number 4 here is a pretty tricky one. I see the people who have completed this assignment already. I don't think anybody's gotten this one right yet. The limit as x approaches -1 of f of x. So the key thing is we're going to treat this like number 3. We're going to work inside out. So the first thing we have to find is the inside function here, f of x. What is the limit as x approaches -1 of f of x? And the answer to that is if we are going to determine through the graph. If we look at the graph, as x gets closer to -1 from the left and from the right, they both approach the same y value, 2. So the limit as x approaches -1 of f of x is 2. The key thing is then we now have to apply that to the inside function. So our next question is, what is the limit as x approaches 2 of f of x equal to? And here's the catch. You will be tempted on the AP test to evaluate that just like you would any other limit from the left and the right. The problem is if you look back at the original, we're approaching 2 from the left and the right from y values that are smaller than 2, right? We're approaching it from like 1.9, 1.99, 1.999 from the left and the right, and we never quite actually get to 2. So the key thing is when you're evaluating the outside function, this is the limit as x approaches 2 from the left, are numbers that are smaller than 2. So we only have to actually evaluate from this direction what we're approaching. And the y value we're approaching from that direction is 5. So the answer to this problem turns out to be C, 5. Okay, so those were a bunch of graphical ones. Now we're going to kind of shift gears and do some more analytic ones. In order to find these, the first thing that you should always try is direct substitution. See if you can plug in whatever value that they give you into your function. So if we plug in -3 here to find its limit, we're going to do the -3 squared minus 9 over -3 squared minus 2 times -3 minus 15. And on the top, that's 9 minus 9 is 0. And on the bottom, that's 9 plus 6, which is 15, minus 15 is 0. So the limit of x approaches -3 is 0 over 0, or an indeterminate form, which means it can't really tell us what the actual limit is. So if direct substitution does not work, then the second thing that you want to try is simplifying. And the most common one that you'll do for these, where it's polynomials, is to factor and see if anything cancels out. If we factor this, we'll get the limit as x approaches -3 for the top, x squared minus 9. It factors into x plus 3 and x minus 3. And at the bottom, x squared minus 2x minus 15, that'll factor to x plus 3 and x minus 5. And what you'll notice in that is that the x plus 3 factor is in the numerator and the denominator. So we could cancel it out and leave us with x minus 3 over x minus 5. And now if you try direct substitution and plug in -3 for x, you'll get -3 minus 3 over -3 minus 5, which is -6 over -8, which is the same thing as 3/4. So again, always try direct substitution first, but if that fails you, the next thing that you should try is simplifying, which you'll do mainly 3 ways: by factoring out and dividing. If there's a radical, then you want to rationalize by multiplying by the conjugate of that radical to the numerator and the denominator. And then there's some identities that you need to know as well, like the sine of x over x is 1. Okay, number 6. X squared minus 1 squared over x plus 1 divided or times x plus 1 over the absolute value of x minus 1 is the function that we'll use when x does not equal 1. And 2 is the function that function we will use when x is 1. So basically, we use this top function for every single value except 1. And at 1, we say f is 2 instead. If what we need to do is find the limit. In order to find the limit, again, you have to find two things. The limit is going to be the value of y that you approach from the left and the right of your function. So we need to find the limit as x approaches -1 from the left and the right. And there's, again, a number of ways you could do that. You could, if you like the way we did graphing above, you could go back and use your TI-84 to graph it in order to find out what the limit is. If you don't like that, what you could do is you could make a table like we did in number 3. And your graphic calculator can really generate that table for you and look at x values as you get closer and closer to -1. But the key thing here is you have to understand you can do this algebraically if you understand what a piecewise function is that has an absolute value. That absolute value is really just another piecewise function. And to determine what that piecewise function is, we have to say, well, when is the absolute value here? 0. What values of x is going to make that 0? And that is going to be at x equals 1, which you get a strong hint that there is a problem at x equals 1, right? So that sometimes your AP test will actually help you in its instructions for finding out what that breakpoint is. Because the key thing about an absolute value function is all that does is when your value is negative, it makes it positive. And if it's positive, it just stays the same. So we can say that basically this function is the same thing as the x minus 1 squared x plus 1 over negative x minus 1 when x is less than 1. And it's just the actual function, x plus 1 over x plus 1, over x minus 1, when x is greater than or equal to 1. At greater than or equal to 1, right, it's 0 or a positive number, and the absolute value doesn't do anything. At less than 1, all you have to do is put that negative sign in there because that's all an absolute value function does, is it takes a negative and turns it into a positive. And then, so we're going to find the limit as x approaches 1 for this left side and for the right side. For the left side, the limit as x approaches x minus 1 squared of x plus 1 over negative x minus 1. Again, you'll notice that there's an x minus 1 and x minus 1 in the numerator and the denominator, which means we could cancel out one of those on the top with it on the bottom. And we'll get the limit as x approaches -1 from the left, or sorry, positive 1 from the left of negative x minus 1 times x plus 1, which you can do through direct substitution. And if you plug in 1, you're going to get 0. And now if you do that for the right side using this, you're going to get the exact same thing. The limit as x approaches 1 from the right of x minus 1 squared x plus 1 over x minus 1. Again, there's an x minus 1 in the numerator and the denominator, right? So we can cancel out one of the ones in the numerator with the factor in the denominator, which leaves us with the limit as x approaches 1 from the right of x minus 1 times x plus 1. Notice that the only thing that changed between the left and the right side was on the left side we had this negative to worry about. On the right side we don't. But if you directly substitute now, you'll still get the same thing. 1 minus 1 times 1 plus 1 is just 0. So the limit as we approach from the left is 0. The limit as we approach from the right is 0. Those both agree. So the limit exists, and we say that it's 0. That's kind of a tough one. All right, number 7 is your squeeze theorem problem. So we have g is the sine of pi over 2x. plus 4, and h of x is negative 1/4 x cubed plus 3/4 x plus 9 over 2. So the key thing that tells you this is squeeze is this right here, and this right here. So the idea here is that between negative 1 and 2, f of x falls between or is squeezed by the functions g of x and h of x. So if the limit of x approaches 1 of g of x and h of x agree, then f of x will have to agree to be that same one as well because it is squeezed between g and h, right? So like if you imagine, okay, this is just a rough sketch, but if you imagine like this is g of x, it's always lower, h of x is always higher, but if they can agree at this point where x approaches 1, then f, no matter what it was, will have to approach and agree at that same point as well because it is always between g and h. So in order to find this problem, we just need to find what is the limit as x approaches 1 of g of x. Well, let's try direct substitution. What is the sine of pi over 2 times 1 plus 4? Which is the sine of pi over 2. And if you remember unit circle, pi over 2 is like at 90 degrees, which has a y value of 1 plus 4 is 5. If we do that for h, the limit as x approaches 1 of h of x, if we plug that in, we'll do negative 1/4 times 1 cubed plus 3/4 times 1 plus 9 halves. And that is going to be what? 2/4 plus, or 1/2, I could say, plus 9 halves, which is 10 halves, or 5. And so since g and h agree, then the limit as x approaches 1 is going to be 5 for h and 5 for g, which means no matter what f is, if it has to stay between g and h, then it will have to go to 5 as well at x equals 1. So the answer is C. All right, number 8. So we have this huge piecewise function, and the question is which of these is false? All of these prompts are talking about continuity. So let's review what it means to be continuous. A function is continuous if the limit as x approaches a value as a continuous at a point c, if the limit as x approaches c from the left of f of x is the same thing as the limit as x approaches c from the right of f of x. And that actually is the value of f of c. So the idea here is, let's do a rough sketch. The idea is if I have this function, as I approach from the left, that has to be the same y value we approach from the right, and that point actually has to be f of c. So that's the difference. In order for the limit to exist, all that has to be is the left and the right approach the same number. In order for it to be continuous, it has one extra criterion. The number they approach actually has to be the value of f of c. So if we look back at these ones in the past, this one right here, for example, this is not continuous at x equals 2 because the limit as we approach x from x equals 2 from the left is 4 and the right is 4, but the actual value of f of 2 is really 1, right? It's not 4. So this is not continuous. But let's say here at 0, it would be continuous because the limit as we approach 0 from the left is 0, the limit as we approach 0 from the right is 0, and the actual value of f of 0 is 0. And that would apply at like 3 and 4 and basically every single point on this function except for at that hole. This one would be discontinuous here, and here, and here. This one would be discontinuous here, and here. This is what we would call a removable discontinuity because all there is a hole in the graph. This would be called a jump discontinuity because the removable one, the limit exists. They approach the same value. But for the jump in discontinuity here, it doesn't. The limit from the left and the limit from the right don't agree. The limit from the left is 5, limit from the right is 2. Okay, so back down to here. Now that we know that, what we're asking then for each of these numbers, what is the limit as x approaches whatever the value is from the left, the right, and then what is the value? So if you can make like a quick table to run through all of these. This is c from the left, this is c from the right, and this is actually f of c. So let's do the first one. At 1, as we approach 1 from values less than 1, we're going to use this first one. And if we find the limit as x approaches 1 from the left of 2x plus 3, again, always try direct substitution first. That would be 2 times 1 plus 3, which is 5. So the limit as we approach from the left is 5. The limit we approach from the right is going to be determined for values where x is greater than 1, which means we're going to use this third one. And again, you could just use direct substitution. If you plug in here, negative 4 times 1 is negative 4, plus 9 is 5. And then the actual value at 1 is 5 as well. So it is true. It is continuous at x equals 1. And remember, we're looking for where is it false. So where is it not true? All right. So the first one is not going to be the answer. It is true. Let's check if this one is false. So now we're going to look at 2. Well, for our function, 2 falls between 1 and 3, which means it uses this linear equation. And all linear equations are continuous, right? So at this point, we could already know, but if you plug in the limit as we approach 2 from the left, we would use the negative 4x plus 9 equation. And using direct substitution, negative 4 times 2 is negative 8, plus 9 is 1. Negative, and that would be the same thing for the right. And the actual value when we plugged in, we got is 1. All right, but negative 3, you can already tell that this is not going to work. Let's see why it doesn't work. As we approach 3, so 3 is another part where this piecewise function diverges. As we approach from values less than 3, we're going to use this one on the left. So if we directly substitute in, negative 4 times 3 is negative 12, plus 9 is negative 3. And you'll notice that that is not the same thing as the value of x at 3. The value of x at 3 is 4. So you can already tell it's not continuous. And if you found the value as we approach from the right, where x was greater than 3, if we plug that in, 3 minus 6 is negative 3. So although the limit exists here for this one, it is not continuous because the value as we approach from the left and the value as we approach from the right are not the same thing as the value at f of c. So the answer is C. For number 9, which of the statements is true? So in order to do this one, you have to look for discontinuities again. So if you scroll back up, the idea is that discontinuities are only going to happen. Oh, actually, I don't know if I wrote it in this one. I think I just put in somebody's comments. Discontinuities will happen in a function like this when the denominator is 0. So if we look at that, where is the denominator going to equal 0? If we set x squared minus x equal to 0, it would occur at 2 points. And you can tell that by factoring. First of all, they both have an x. So if I factor out the x, what I'm left with is x minus 1 equals 0. And that's 0 at 2 points. When x is 0 or when x is 1. So those are both going to be points of discontinuity. Now to find what type of discontinuity it is, we have to look and see whether or not we could remove one of these discontinuities. And in order to remove a discontinuity, you have to be able to simplify it and reduce, cancel out with a factor on top. So if we factor the numerator here, you'll notice that they both have in common an x squared. So the factors for the numerator could be x times x, which would leave us with 3x plus 2 over x times x minus 1. And you'll notice that this factor of x could cancel with one of the x's on top, making it a removable discontinuity. But there is no x minus 1 factor to cancel out, so this is not going to be a removable one. Now the question becomes whether or not it's an asymptote or jump discontinuities. Jump discontinuities will generally only occur because of those piecewise functions, like we see in this one, where on the left side we're using like a quadratic function here, but on the right side we use a linear function that starts at a different spot. So that is going to be a vertical a discontinuity due to a vertical asymptote. And if you're not sure about that, you could always check it by graphing it in your TI-84 and looking at it. But the idea here is it's only a jump discontinuity if the limit as x approaches c from the left or the right is going to approach some value y. It is a vertical asymptote is if you approach from left to right, it approaches infinity. And if you know your rational functions and you know generally what causes those things to be true, jump discontinuities are generally due to piecewise functions, and vertical asymptotes generally occur when you have a rational function like you have here, where there's a fraction in your function with a x in the denominator. Okay, number 10. So again, this is what I was talking about. If you know your types of functions here, then then you really don't have to show a lot of work for this one. This first one is A is continuous over its entire domain. It's a polynomial function. They are continuous over their entire domain. C is a periodic function. It's a trig function, cosine, where it looks like this. Right? It just bounces up and down between 1 and -1, and it is continuous over its entire domain. This one right here and this one right here, B and D, are suspicious. So these are the two you should look at. And again, your question is what will create a discontinuity is when the denominator equals 0. So we have to ask, can x squared plus 3x squared minus 2x minus 5 equal 0? And almost certainly, right? That's a cubic function. Cubic functions look like this, which means that they have a range from negative infinity to positive infinity. So there is going to be some y value that makes it 0. If we double check our work to make sure B is the only one that can be discontinuous, and we ask for D, what value makes it a 0 in the denominator? E to the x equals 0. If you want to solve that for x, the first thing you would do is take the natural log of both sides, where x is equal then to the natural log of 0, but you can't take a natural log of 0. So this cannot equal 0, which means that this cannot be discontinuous. So D is not an option, which means B is the correct answer. It's the only one that's not continuous. All right. Number 11. So again, we're running into another one of these continuity questions. So the question becomes, if a is a constant, what values of a, if any, is the function continuous at x equals 3? So we want the limit as x approaches 3 from the left of f of x to equal the limit as x approaches 3 from the right of f of x, and we want that to equal f of 3. That's the requirement in order for it to be continuous. To determine the limit as x approaches 3 from the left, we want values less than 0, which means we're going to use this function, a squared plus x squared. And for the right, we will use values greater than 3, which means we're going to do the limit as x approaches 3 from the right of ax plus 3. And then the value of x at 3 would use that same function. So I'm not going to write it again, right? This is for x is greater than or equal to 0, greater than or equal to 3. So, I mean, I guess we can write it. That's going to be a times 3 plus 3, or 9a. So the question becomes, if we want this and this to be the same thing, to equal 9a when we find their limits. And how do you find a limit? First thing you should always try is direct substitution. So we're going to plug in 3 into our functions here and see what we get. So we want a squared plus 3 squared to equal a times 3 plus 3. So in order to do that, we will get a squared plus 9 equals 6a, and we want those to equal, and we also want it to equal 9a here, or yeah, okay. We'll ignore that part for now, and we'll use that to double check our answer, I think is the best way to handle that. So if we solve this for a squared plus 9 equals 6a, and plug that in, a squared, if we minus 6a from both sides, plus 9 equals 0, is a quadratic. And if we solve that, it'll solve for, by factoring, we could do, I feel like there's something in this problem I have messed up. For what values of a, if any, is f continuous at x equals 3? Yeah, so we just want those to equal when x is 3. Oh, I think we got it. I think the only time those will equal is 3. Oh yeah, no, I'm sorry. Okay. Yeah, if you factor that's a minus 3 equal, I didn't mess up. It's just, if you factor that, you get a minus 3 squared is equal to 0, which is n equals 3. So if we plug that in, oh yeah, here's where I messed up. Yep, 3 plus 3 is 6. I was like, this is not going to work when I go to check. Yeah, sorry, 3 plus 3 is 6, not 9. So this should be 6a equals 6a. Yeah, so again, you could just ignore that and really use it to check your answer at the end. Or sometimes when you check your answer, it'll mess you up, and then you have to go back and check your check. So anywho, yeah, if you try to check the limit from the left and the limit from the right, when you directly substitute 3 in for x, you'll get a squared plus 3 squared on the left, a times 3 plus 3 on the right, which gives us a squared plus 9 equals 6a. Subtract 6a from both sides. It's a quadratic, which factors into a minus 3 squared, which is 0 when a equals 3. So the answer is 3 only. Sorry about any confusion there. Okay. I bled over into the next problem here. For the next problem, our question is an FRQ. And for these FRQs, you could type up your answer in a doc and submit it, or you can like write your answer on paper and then take a picture of it of your phone and then attach the phone. You could do pretty much whatever will be comfortable for you for that. So we've got the let f be a function given by f of x is ln of x over x for all x is greater than 0. The derivative is that. Find the limit as x approaches 0 from the right. So in order to do that, we would directly substitute. Our first thing we would try is direct substitution. If you do the limit as x approaches 0 from the right and directly substitute, you'll get the natural log of 0 over 0, which doesn't tell us anything because that's not in the domain. We can't take the natural log of 0. So the next thing that you could try then is to graph it, or to make a table and just do values as you get closer and closer to 0 from the right. So good candidates to test would be 0.1, that's 0.01, that's 0.001, and so on and so forth if you needed to in order to find out what that is. And if you do that, let's just pull up a calculator really quick. Oops, sorry. So if we do 0.1 and take its natural log and then divide that by zero point 0.1, you'll get negative 23. If you do 0.01, so 0.01's natural log divided by 0.01, you'll get negative 460. And if you did 0.001, divided by 0.001, you'll get negative 6900, and then 6907, and you'll notice that that approaches, it's just getting lower and lower. So we're going to say that it approaches negative infinity, so that all you needed to write in order to get your answer here, or your 1 point, is that. And again, you could have also done that by graphing. So if you go to like desmos.com, or if you use your TI-84 and you just start graphing, and type in the natural log of x over x, you'll see that as you approach 0, it gets smaller and smaller. It just approaches -1. All right, number 13. So for this one, we have a continuous function. For 0 to 13, what is the fewest possible number of times x would equal 4? So this is the intermediate value theorem. If you have a continuous function, then for every y value that is squeezed between an endpoint, two endpoints that have like a lower and a higher y value, it will have to cross that y value in order to get to the other. So like, let's draw another sketch. So if this is your first endpoint and this is your second endpoint, and you need to get from here to here between certain values, like between 0 and 13 for x, every y value that's between these two y values is going to have some value between 0 and 13 that makes that y value. It would be impossible for me to get to this endpoint to that endpoint without crossing every single intermediate value between those. So for example, between 0 and 4, I go from 3 to 4.5. So between 0 and 4, there must be a value where I would have like 3.5 and 3.6 and 3.7 and 3.85. Every single number between 3 and 4.5 will have some x value that produces that output. So our question is, how many times must we produce the number 4? So really, the mechanics of this are not too bad. I'm just looking for, when does 4 fit between the interval? So between this interval, yeah, 4 is between those numbers, so that it will have to pass through, f of x will have to pass through 4 at least once to get from 3 to 4.5. The next interval, is 4 in between those two? Yes, it is. So in order to get back down from 4.5, or to get from 4.5 back down to 3, we will have to pass through 4.1 and 4.05 and 4. So there's a second time. From 3 to 2.5, it is possible that it could go from 3, dip back up, and then go back down, but it doesn't have to, which means that if we're looking for fewest, we're not going to count that one. And then from 2.5 to 4.4, 4 is between those two numbers, which means, again, for some x value between 8 and 13, there must be a y value that is 4. Otherwise, it would be impossible to get from 2.5 all the way up to 4.4. So this is the third one. So the answer is 3. So really, it's just understanding the intermediate value theorem is that as long as you are have a continuous function on your interval, on the closed interval from 0 to 13, that if you look at your y values of 0 and 13, there is going to be a value between 0 and 13 for x that will produce an output between whatever fits in your range here. All right, last question, 14. So For part A, we're asked to find a tangent line. In order to find a tangent line, there are two things you have to find: slope and a point. In order to find the slope, we use the derivative. And look, they give us the derivative right here. The derivative of y with respect to x is 10 minus 2y. So to find my slope, I'm just going to plug in for the point that they give me, 0, 2, I'm just going to plug in those values. So if I plug in 0 for x, there is no x in the equation. But if I plug in 2 for y, I'll get dy over dx is 10 minus 2 times 2, which is 10 minus 4, which is 6. So the slope is 6. And then my point is 0, 2, right, which it gives me right there. So then I can write that y is equal to 6x plus 2. And then to use that to approximate f of 0.5, I'll just plug in 0.5 for x. So I'll do y at 0.5 is 6 times 0.5 plus 2, which is 3 plus 2, which is 5. All right. So for this one, it was worth 2 points. 1 point if you got that the slope was 6, and then, or sorry, if you needed to get the slope was 6, and then actually write the equation y equals 6x plus 2. They would have also accepted y minus 2 equals 6x minus 0. If you just left it in point slope form, that would have been fine. And then you would get the second point for, again, plugging in 0.5 and getting 6 times 0.5 plus 2 is equal to 5. All right, part B. In part B, we're supposed to find the second derivative, d squared y over dx squared at the point x is 2. So in order to do that, what you're going to do is take the derivative. I think I'm going to write this down here. The derivative of dy over dx equals uh, 10 minus 2y. Is that the equation? 10 minus 2y. Of 10 minus 2y. All right, to do that, the derivative of dy dx is d squared y over dx squared. The derivative of 10 is a constant, it's just 0. And the derivative of negative 2y is negative 2 dy dx, right? If this is the chain rule, the negative 2y, the outside function negative 2 has a derivative, or of 2y has a derivative, would be the power rule. You take the power of 1, multiply it down, negative 2 times 1 is negative 2, and then you subtract 1, you get y to 0. And then the derivative of y with respect to x is dy dx. But you're not done, because what is dy dx? Well, dy dx is just 10 minus 2y. So you could tell me that the second derivative of this function is just negative 2 times 10 minus 2y, or 4y minus 20. All right, the second thing that we're asked to find is its concavity. So in order to find whether or not it's concave up or down at the point 0, 2, we're going to plug in the point 0, 2. If you plug in 0, 2, the derivative at 0, 2 is would be 4 times, instead of y, we put 2 minus 20, which is 8 minus 2, which is, or 8 minus 20, which is negative 12. Since negative 12 is less than 0, then we say it's concave down. And so the sentence they put here would get you full marks on this problem. But basically you want to say, because the derivative, the second derivative at 0, 2 is negative, and because the function is continuous, then the graph is concave down at the point 0, 2. And then that one would have got you 2 points. One for finding the first derivative, and then one for saying that it's concave down with that explanation. All right, part C, we need to find the particular solution. This is actually a pretty tough problem. This is what we were doing before the end of spring break. And in order to do this, you have to do these steps to get all the points. You have to separate your variables, y's to the left, x's on the right, which in our case, we won't have x's. So really, we just need to move the y values to the left. And then we have to take the antiderivative and then make sure you put the plus c when you're doing the antiderivative, and then use your initial condition of 0, 2 to find the value of c, and then solve it for y. So here's what that looks like. So our equation was dy over dx is 10 minus 2y. So I need to move this part over to the left, and I need to move the dx over to the right. And if you do that, you'll get this. 1 over 10 minus 2y dy equals dx. You then need to integrate both sides. The antiderivative of 1 minus 10 over 2y is the negative 1/2 natural log of 10 minus 2y. And you could do that using u substitution. If you say u is 10 minus 2y, then du is negative 2 dy. And then since there isn't a negative 2 in the numerator, you have to move the negative 2 to the other side by dividing. So you'll get negative 1/2 du is the same as dy. We'll plug this in for dy. We'll plug u in for 10 minus 2y. So you'll get the integral of uh, negative 1 over 2 of du over u. And the negative 1 over 2 could just move out in front. And the antiderivative of a variable in the denominator is just the natural log of that variable, or the natural log of the absolute value of that variable. And then if you substitute back in, u is 10 minus 2y. So we plug that back in, and you'll get this third line that they got here. And make sure on the right side here, when you're doing the antiderivative of 1 is just 1x plus c. If you don't have that c there, you lost an entire point because they need the constant of integration whenever you take that antiderivative. So to find out the value of c, what we have to do is plug in 0 for x and y for 2, which they do in this slide right here. And then you have to do some algebra in order to solve that. You'll get 10 minus 2 times 2 is 6. So c is the negative 1/2 natural log of 6. And then you'll plug that back in. So if you remember to your function, so instead of then negative 1/2 natural log of 10 minus 2y equals x plus c, we now know c is negative 1/2 natural log of 6. So we're just rewriting this same thing right here with negative 1/2 natural log of 6 instead of c. And then you need to solve this for y. In order to do that, the first thing that I would do is multiply both sides by negative 2, which will give you the natural log of 10 minus 2y equals negative 2x plus the natural log of 6. And then you need to get, in order to get y by itself here, you need to get rid of this natural log. And the opposite of taking the natural log of something is to raise it to the power of e. So we'll get on the left side 10 minus 2y, but on the right side e to the negative 2x plus the natural log of 6, which the natural log of 6 and e will just really cancel out, and you'll be drop that 6 down in front as a power, right? E to the natural log of 6 is just 6 because the e and the natural log cancel out. And if you have e to the negative 2x plus, or sorry, and then the e to the negative 2x you'll just leave as it is. So that'll give you that. And then if you then solve the rest of this for y, you would subtract 10 and then divide by -2. And that'll leave you with 5 minus 3 e to the -2x. All right. Part D then tells you to find the limit of that function. So we're going to find the limit as x approaches infinity of the function you found in part C, which if you plug in infinity, or if you think about plugging in infinity, e to the negative infinite power here is going to approach 0. -3 times 0 is just 0, so the answer is 5. All right. Hopefully this video will help you on doing your problems. If you have any questions about anything that came up in this, please feel free to email me. There'll also be, I believe, on Wednesday of next week, there'll be office hours where I will try setting up a Zoom meeting and see if that gets any interest. There needs to be at least 2 or more students in order for me to hold that Zoom meeting. If there's 1 or 0, then I won't record anything. I'll just assume you don't have any questions over the content. Part C, I'd say, is probably the hardest part of this whole thing. As far as content for the rest of the semester, we only have to learn about 2 lessons that I think we need more instruction on, and that is separation of variables and L'Hopital's rule. We will pick those up probably in about 2 weeks. We'll do maybe 3, depending on how fast we can go, some instruction like that. But after you've received that instruction, then I think you have covered everything that's on the AP test in our class. So we'll just go back to reviewing. If there's interest, also, I might put up a Zoom lesson for this Friday, but we'll see. All right, well, thank you all for watching, and I will hopefully see you when I see you.